So I want to work all these problems in this section just because they are sometimes a little bit difficult to keep all the steps straight. So this is going to be problem number 32. And 32 says, find the limit of S of n as n approaches infinity. So S of n is, what that is a sum. And it's a function of n. And and as we have, less numbers, then as n is smaller, then we get something. And then as you increase n, it's going to approach some value. And you could actually do it as a spreadsheet just to see physically what happens. Let's try to decide. I'll do that at the end. So if you're interested, you can watch the rest of it, but otherwise you don't need to. So what we're looking at is, what is the limit of S of n as n approaches infinity? So the way to work this out is we're going to multiply all these three terms together and get a new expression. So we'll still have 64 over n cubed here at the beginning. And the numerator will become this times that, so it'll be n squared plus n. So let me just write that in small. So we get n squared plus n from the first two, and we multiply by 2n plus 1. So we use FOIL. So we end up with 2n cubed from the first. N squared times 2n gives us 2n cubed. From the outer we get n squared. From the inner we get 2n squared. And from the last we get n. It's all divided by 6. Okay, combine like terms. So we get 2n cubed plus 3n squared plus n divided by 6. And that's S of n, so we have to take the limit as n goes to infinity. We're not going to do that until we simplify it. I haven't gotten to that point yet. Okay, so we're going to take the limit of that, and I didn't write it in here, but basically we're taking the limit of both sides. This is going to give us some number. Now, the last thing, so I'm going to write it in here. Limit as n goes to infinity. So 64 divided by 6 is equal to something. I'll get my calculator out. It doesn't have to be a nice even number because 60 divided by 6 would be 10, and 66 divided by 6 would be 11, so it's something else. We're not going to do that until we get to the end. Okay, now each one of these terms we're going to divide by n cubed. So we'll have 64 times 2n cubed divided by n cubed plus 3, and let's put the 6 out here for the time being, 3n squared divided by n cubed plus n divided by n cubed. You see we can, n cubed divided by n cubed is 1. So we get 64 over 6 times 2 times 1 plus 3 times 1 over n. If you simplify it, we divide both the numerator and the denominator by n squared. We get that, and then the final one is we get 1 over n squared. So we divide this by n, we get 1. Divide that by n, we get n squared. And now we can take the limit as n goes to infinity, because this will go to 0. 1 over infinity is 0, plus 1 over infinity squared is 0. So the only part remains is that part. So now we've taken the limit. So at least when we take the limit, this goes to 0. this goes to 0. We're just left with the number, so we get the answer is 64 times 2 over 6. And so 64 times 2 divided by 6 is still a fraction, but it's 128 over 6. If we divide both by 2, we get 64 divided by 3. So that would be your final answer, 64 thirds. Okay, so I've checked it. That's correct. And that's what happens with these sums is that we end up with some expression like this, and then we cancel out things and we simplify it, and we usually end up with some constant plus these fractions which go to 0 and goes to infinity. That's the whole idea behind this situation. Okay, the next problem is 39. So what we're doing is asked to find the limit as n goes to infinity of this formula. Limit as n goes to infinity of the summation. So what we end up with in these kinds of problems is we end up with a summation because we're adding up all these little areas. So this is not actually the integration part, but this is just an example of the kind of expression that you'll have to evaluate. Okay, so 16 is a constant, so you can bring that outside the summation. So you just times 16 times the summation is the same as the summation of 16 times, just like you can take the constant outside the integration signs. And n, when you specify n, it's a constant as well, so that goes out. I mean, ultimately, we're going to let n go to infinity, but as far as the summation is concerned, if n was equal to 10, then we can move these both outside of this summation sign, so we can do that. And so we get 16 over n squared times the summation of I equals 1 to n. So what's this? Is just 1 plus 2 plus 3 plus 4 plus 5 to n. You add all this up, and there's a formula for that particular operation. So we go look for it, and let's see. That's on page 260. If you look at page 260, summation formulas, equation number 2 says summation of I from I equals 1 to n is equal to n times n plus 1 over 2. So we make that substitution for the summation, we put in that, which is based on the fact that, if you have all these numbers, say let's 1, 2, 3, 4, 5, 6, you can match these up, and you'd have 1 plus 6 divided by 2. Actually, is you add these together, and then you keep matching them up, so you get 6, or 1 is 7, 2 and 5 is 7, 3 and 4 is 7. So that's like 3 times 7. So that's the way it works, and you can go with this formula. So now the original limit becomes 16 over n squared times the summation. In terms of n, it's n times n plus 1 over 2. What we do is just like in the previous problem, is we multiply this thing out. We're going to have 2 terms. So let's put 16 out front, and in the numerator you're going to have, actually let's bring the 2 out as well. So I'll put that 2 from here. And then inside the parentheses we're going to have n squared plus n, that's from here, n times n is n squared, n times 1 is n, divided by n squared. And now we do this division, divide that by n squared and that by n squared. So we have 16 divided by 2, which is 8. And we have 1 plus 1 over n. N squared divided by n squared is 1. N divided by n squared is 1 over n. Then we take the limit as n goes to infinity. Well, this is unaffected. This goes to 0. So what we end up with is just 8 times 1 plus 0. When we do that limit, this 0 is from that term. This 1 is from that term. So we really have 8 times 0. So let me just put that in there so we know where that comes from. So we have 8 times 1 and 8 times 0. And that's equal to 8. So that's the solution. That's the answer to that particular problem. And that was 39. So let me just double check to make sure that's the correct answer. Yes. Okay. Okay, now we're problem 49, which I think is actually where we calculate some areas. Let's get to the page. 49. Use the limit process to find the area of the region between the graph of the function and the x-axis over the given interval. Sketch the region. Okay, so our function is y equals x squared plus 2. Our interval is from 0 to 1. So what we're going to do here is we are going to figure out what is the x of I. So what is the value of x? Well, it goes between 0 and 1. So we have 0 plus the difference between these two, which is going to be 1, divided by n. This is the number of rectangles. So if you had 10 rectangles between 0 and 1, you would have 0 as your first one. So when n is equal to 0, or you could do n equals 1, it doesn't matter, it's just whether it's left or right or left hand, which value you're taking. So let's assume that n goes from 0 to 9 in this case, just as an example. So you break it up into 10 parts. And so x would be 0.1 when n is equal to 1, 0.2 when n is equal to 2, etc., etc. So that's how it works. Now we're going to let n go to infinity at some point. So, but x of I is equal to just 1 over n. Now delta x, so we need a delta x here because what we're looking for is the width of the rectangle. That's the height. That's not the height, but if we plug that into here, it'll be the height of the rectangle. So delta x is just 1 divided by n also. And it's 1 because we have an interval of 1. If we went to 2, it would be 2 divided by n. If it was 3, it would be 3 divided by n. Likewise, this would be 1, 2, or 3, depending upon what the interval was. So that's delta x. So the area is equal to the summation from I equals 1 to n to n. Or we could say I equals 0 to n. I guess it really doesn't matter. N minus 1. But ultimately it'll go to infinity. So let's just say I equals 1 to n. And the function, the height of the rectangle is this. So it's going to be equal to x squared. X is 1 over n squared plus 2. So that's the function. By plugging in for x of I, we put it in here, so we get 1 over n to the squared. And then we multiply by the width of the rectangle, which is 1 over n. And we do that summation, and to get the exact answer, what we do is we take the limit of this thing as n goes to infinity. So the area, the exact area underneath the curve is the limit as n goes to infinity of this summation. So again, this is basically y sub I. This is delta x, which stays the same. Delta x is 1 over n. This is y sub I. We're plugging in x into the equation. Now, so all we're going to do is we're going to so what are we doing? We're going to do now. Oh, that's actually, I made a mistake there. This is I. This is I. So the i's, so this is actually I squared right there. Not 1 squared, but I, because we're going to let n is going to be equal to 10, say, and I is going to be 0, 1, 2, 3, 4, blah, 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 or, yeah. So that's how it works. So this is actually I over n quantity squared. Now, for a given summation, we don't have this on here. N would be a constant, and I would not be a constant. So what we'd end up, I want to put this over here. The limit as n goes to infinity of what do we have? Well, we have this first term times that. So let me put it in here. Summation from I equals 1 to n of 1 over n from here times I over n squared. And then the second term is the summation from I equals 1 to n of this times that. So we get 2 over n. Make sure that 2 times 1 over n, 2 over n. So we have two summations, and then we'll take the limit of those two terms when n goes to infinity. Now I can factor out the n, so what we'll have is the limit as n goes to infinity of, well, the first term we're going to have 1 over n cubed. Where do we get that from? Well, we have n squared, so n times n squared is n cubed times the summation of I squared. So then we have the I squared. So that's the first one. The second one is 2 over n times the summation of 1 from I equals 1 to, I forgot, I equals 1 to n. I equals 1 to n. So if you factor out 2 over n, you just have 1 left. And now we go to the book and look at the formulas up that relate these summations to what the value of n is. So rather than adding all that stuff up, we have special ones. So equation number 1 applies to this. C is 1, so the summation of this is n. And we have I squared. I squared is n times n plus 1 times 2n plus 1 over 6. That's equation number 3. So we get 1 over n cubed, and then we change this summation to the book, n times n plus 1 times 2n plus 1 over 6. And then the second term is 2 over n times this, but that's just equal to n. Okay, now what we're going to do is multiply that out. We actually did that in a previous problem, but we'll do it again. Let's do it on the side here. So when you multiply n times n plus 1, you get n squared plus n. And you multiply that by 2n plus 1. Using FOIL, you get 2n squared, 2n cubed. N squared times 2n is 2n cubed. You get 2n squared plus 1n squared plus 3n squared, and then the last is just n. So we're going to substitute that in there. So we get the limit as n goes to infinity of 1 over n cubed times 2n cubed plus 3n squared plus n all over 6. That's equation number 3. Well, this is equation number 3. Multiply it out, that's what it is. And the second thing we get is just 2, because we cancel out the n's in that second term. Now, if we divide each term by n cubed, for the first grouping, is we'll get 2, 6 times n cubed over n cubed plus 3, 6 n squared over n cubed plus 1/6 n over n cubed plus 2. And this is going to go to 0. This will go to 0 because the numerator has a lower order than the denominator. This is going to go to 1. So we get the limit. Well, actually, we're taking the limit at this point. So this simplifies to 1, and then as we take the limit, those go to 0. So what we'll end up with is 2/6 from this first term, 2/6 times 1 plus 2 from the last term. That's 1/3 plus 2, which is 2 1/3, which is 7/3. So we get 7/3. So let's just check to see what that's right answer is. So the answer is 7/3. Okay, so that's the way it works. So as we let n go to infinity, a lot of terms go to 0. We're just left with constants that we add together and get the final answer. And this is the exact answer. Our last problem is 54. So it's another one just like 49. We have this function y equals 2x minus x cubed. The interval is from 0 to 1. We choose 0 to 1 a lot because it's easier to come up with the intervals. And we're just trying to prove a point in terms of this summation thing. So again, what we do is we would find out what x is. X is a function of some counting term, which is I. So x of I is equal to the left-hand limit, which is 0, plus I divided by n. So when I is equal to n, we get 0 plus 1, and we get, so when I is 0, well, actually, when I is equal to 1, we get 1 over n. And when I is equal to n, we get 1. So these are the values of x on the right-hand side of the limit, on the right-hand side of the interval. So we have I and I said I minus 1. Anyway, so that's what it is. That's the value of x. We need to know what the value of delta x is. Just like the previous problem, it's 1 over, which is 1 minus 0 is 1 over n. So as we increase n, this fraction gets smaller, so then it's 10. The delta x is 1/10. So 10 times 1/10 is 1. If n was equal to 20, we do 1/20th. 20 times 1/20th is 1. So it just breaks the interval up, this interval up into smaller pieces as n gets larger. And then the y value is just going to be equal to this equation with this substituted in there. You can imagine if I didn't have 0 here, if I had, if the interval was from 1 to 2, I'd have 1 plus I over n, and then it would become much more complicated. It would still work out in the long run, but it's just more complicated. So we don't want to make it any more complicated than it needs to be. So y sub I is equal to 2 times x sub I, which is I over n minus x cubed. So we have I over n cubed. So that's the y value. The y value times delta x gives us the area. So the area, and I'm going to leave space here for the limit, is the summation from I equals 1 to n. So we're going to add up all these areas, and the areas are equal to the y value, which is 2I over n minus I cubed over n cubed, basically. So that's the y value. That's the height of the rectangle. The width is 1 over n. So y times delta x gives us a rectangular area. We add up all those rectangles, we get the total area. And to find the exact value, we take the limit as n goes to infinity. If we use anything less than infinity, we get an approximate solution. But when we let n go to infinity, we have the limiting process, which allows us to get the exact value. Okay, so the area is equal to limit as n goes to infinity of the summation of, from I equals 1 to n, of, what do we have? Well, again, we're going to have two terms. We can break it up into two terms. We have the first one, which is 2I over n times 1 over n. So we have 2 over n squared. So we're going to factor that out. So let's do that. So 2 over n squared times the summation of I from I equals 1 to n. So that's this part. The second part, we have a negative sign. We'll have n cubed times 1 over n, which is, so we'll have 1 over n to the 4th power times the summation from I equals 1 to n of I cubed. So that's the way it always works out. You'll factor out all the constants, all the n stuff. You should be left with I or 1 in these summations. Now we have two equations for these summations. So equation 2 says, it says the summation from I equals 1 to n of I is n times n plus 1 over 2. And we have equation 4, which says the summation from I equals 1 to n of I cubed is equal to n squared times n plus 1 quantity squared over 4. So we can make these substitutions into there. So we still have our 2 over n. This is going to be n times n plus 1 over 2. So for this summation, I'm substituting that. The second part is 1 over n to the 4th times this, which is that. So we get n squared times n plus 1 quantity squared over 4. Now, we're going to multiply these out and see what we get. So we're going to, we'll have the 2's cancel out, so we can just don't have to worry about that anymore. We get n squared divided by n plus, so that's this part, n squared divided, and then we have n divided by n. And actually this should be squared. I know I had something wrong because I didn't have it working out right. So okay, so that's n times n is n squared divided by n squared. And then we have n divided by n squared. And the second part, so let's do this separately. Find out, one thing was we can cancel that out with the 2 of those, so we got just n squared in the denominator. And if we multiply out n plus 1 squared, that's the same as n plus 1 times n plus 1, which is n squared plus 2n plus 1. Okay, so we'll have this divided by that. So let's go ahead and put it in there. So let's divide it by n squared, divided by n squared, divided by n squared. And what that leaves is 1 plus 2 over n plus 1 over n squared. If I divide each one of those terms by n squared. So now we go back here, we have negative, we have the 1/4 times this divided by that, which we just figured out to be as 1 plus 2 over n plus 1 over n squared. Okay, so again, n squared over n squared. N times 1 is n over n squared. Negative 1/4 times the ratio of these, that, and that. This multiplied out gives us n squared plus 2n plus 1 divided by n squared. So this match becomes 1. This match becomes 2 over n. This becomes 1 over n squared. Okay, now we're going to take the limit as n goes to infinity. What happens? Well, n over n squared goes to 0. 2 over n goes to 0. 1 over n squared goes to 0. So these terms get knocked out. And what we have left is just this term, which is 1. That's 1. So we get 1 plus 0 from this term minus 1/4 times 1 plus 0 plus 0. This goes to 0, that goes to 0. So 1 minus 1/4 is 3/4. So that is the area underneath the curve, 3/4. And let me just check to make sure that's the correct answer before we declare victory. So that's problem 54. And we get 3/4. So that's correct. So let's see what we did again. We have our original equation. Here's our interval. We say that the x value can be incremented between 0, which is this, and 1 by saying have I, which is our counter, divided by n. So when I equals 1, we get 1 over n, I equals 2, we get 2 over n, etc., etc., etc. This can be dropped, and we just have I over n as the x value. The delta x, which is the width of a rectangle, is 1 over n, because the 1 comes from this minus that. 1 minus 0 is 1. N is how many times we break it up. So that's the delta x. This is the y value, which is the height of a rectangle. This is the width of a rectangle. So to get the height, we plug in x, with the counter x, which is I over n. So instead of 2x minus x cubed, we have 2I over n minus x I over n quantity cubed. And then we multiply these together to get the area of the rectangles. We add up all the little rectangles, and then we let the number of rectangles go to infinity. And so what we did is we factored out 2 over n squared. There's another n right there. So n times n is n squared. We have a formula for that. We factored out 1 over n to the 4th. We have I cubed. We have a formula for that. Plug those in. Multiply everything out. Simplify it. And you end up with constant terms like here and here. And you end up with terms that go to 0 when you let n go to infinity. So you end up with just 2 constant terms added together, and you get the solution.